I'm Russ Altman, and today Professor Tsachy Weissman tells us that our reliance on information storage, like in our computers, our phones, hard drives, and in the cloud, is a threat to the environment and why we need new ways to make information compact for storage. We also need new ways to store information, even possibly including biological molecules. It's the future of data storage and compression. You know, many of us don't think very much about where our information is stored. You know, we think about, okay, our cell phone has information, there's a memory in our computers, we have hard drives, and then there's this thing called the cloud where we keep a lot of our information. And we're generating data exponentially, increasingly every year, more and more. Now, what we don't think about is that the cost of storing this data is increasing as well. Why? Well, there are huge farms, they call them computer data farms, where large amounts of computers sit in rows in big buildings, using energy and storing all of our data. It turns out that there's enough of these farms now that they're starting to have a measurable impact on the environment. They use a lot of power, they generate heat, and they generate greenhouse gases. Yikes. So there's a lot of problems just with the basic storage of all the digital data being generated in the world. Now, there are two main approaches to fixing this. First, you can figure out how to more efficiently compress our files into smaller and smaller file formats so that you can get the file back and expand it back to its full image or full document, and that's called compression. The other thing you can do is you can find entirely new ways to store information. So remember, we used to have floppy drives and then hard drives and then CDs and DVDs. What is the next generation of storage going to look like? Professor Tsachy Weissman is a professor of electrical engineering at Stanford University. He's an expert in information theory, and he uses these theoretical foundations to develop new algorithms for compressing information, the next generation of JPEG or MP3 or MP4. He also explores new media for storing information so that we can get on top of this problem that's generating some environmental hazards. I will first ask Tsachy to describe the critical issues in information storage these days and why we should care about how our files are stored.
Well, I think humanity is reaching a point where the storage of our information is the true bottleneck. We've developed all these amazing technologies that allow us to gauge the world around us extremely exquisitely with high resolution, if it's in biology and genomics and astrophysics and VR and AR and the new emerging types of point cloud data, in the context of the metaverse and so on. And the main problem is now not the acquisition and measurement of all of these types of data, but in their storage and where you put these data, and then how do you manage it and how do you access it to get the kind of insights and the kind of benefit that you wanted to begin by capturing these data.
So this is super important because I think all of us are aware that sometimes these paper records from 50 or 100 years ago seem more stable, reliable, available. So do we have a crisis in terms of the likelihood that important historical records, documents, things that people might want in the past will even be available?
Absolutely. I think it's a crisis on multiple levels. Number one, people I think don't recognize just how vulnerable our current systems for storage information have become. People think that, you capture whatever it is you care about these days and you don't put it on paper, you upload it to the cloud. And yes, it's sitting in a bunch of servers, usually shredded and then, kind of sent all over the place, all over the planet, essentially, in ways that are kind of redundant and eventually reconstructible with high probability. But, everything is potentially error prone, and there are increasing ways in which someone malicious, for example, can hack the data, can disrupt it, can delete it. So, yeah, in terms of important information that humanity needs to store long term, I think we are definitely in a place where we need to be thinking much more seriously and carefully about the ways in which we store these data. And it's more, I think, acute than it was like a generation ago, where the storage was maybe, in some senses, less scalable, but much more controllable.
Yeah, so and I know you've written about how the arrival of the cloud kind of changes things, and I would have thought it would have changed things in good ways. Like, okay, now I just send stuff up to the cloud. Some set of professionals are thinking about how to back up my data and to make sure it's secure, and then as long as I keep paying them, they won't delete it. But I believe that you've written about the cloud is actually a much more complicated challenge as you look at these issues.
Yeah, I don't know that I've written too insightfully about this specifically, but I do feel that it's this sort of mode of putting everything on the cloud. It comes with many benefits, but it's also something that humanity will have to at some point sort of come to terms with the limitations and the toll that this mode is taking on the planet. I think many people, even those who care about, the greenness of our storage technologies, they don't necessarily think twice about capturing lots of data, taking 30 images of their grandkids, and they think it's all fine because they don't feel the pain of the storage. It's all somewhere on the cloud. But in the end, all this data is just information. These are bits stored as different voltage values, and how they have to be maintained in these really large server farms that are taking increasing fraction of the area of this planet. They're taking a lot of material resources to build. They're taking a lot of energy to maintain the right temperatures, the right voltage levels, and this is becoming actually a growing fraction of humanity's carbon footprint. And if things continue at the current rate, which by the way, currently they seem to be, even the rate seems to be potentially increasing because of all these new emerging data types that people now want to pursue with increasing resolution. I think, very soon humanity is going to have to rethink the ways in which we kind of store and represent our data.
Yeah, so I think a lot of people would be surprised to hear that it's already a point where you're telling us that there are measurable impacts on the environment because of things like the cloud computing centers that are holding the data, and that, just to repeat what you just said, that this will become a critical problem probably a lot sooner than people realize. So this is what you're an expert at. So how does this inform your research? What are the big opportunities to fix this problem?
Well, my research is both sort of theoretical and much of it is academic. So I have just all sorts of fun with students and colleagues at Stanford, thinking about potentially completely new ways to represent our data, both in terms of sort of new types of algorithms for compression of information of all sorts, from genomic through
and when you say compression, just for people who don't think about this, you literally mean taking a 1 megabyte file, like a text file or a picture, and squeezing it so it's way less than 1 megabyte. And that's what compression is. And obviously, if you can compress things more, they won't take as much space up, and therefore not as much electricity, not as much environmental impact.
Exactly. Think of an analogy of, compression of real things. Like you have a bin of garbage, and, you can just sort of take that garbage and start squeezing it and making it much tighter. And that becomes much more efficient and then also, potentially very directly is good for the planet. And in fact, now storage in bits, I view it as becoming increasingly similar, not only conceptually, but also physically, to compression of our garbage and of the kind of things that we need to recycle.
So, how good are our compression algorithms currently, and do you see a lot of room for improvement, or have smart people really smushed the garbage as much as it's going to be smushed?
That's a good question. My feeling is actually every place I look for every type of data that I sort of kind of try to roll up my sleeves and look carefully, from genomics to multimedia, I feel like there's substantial room for orders of magnitude improvements, which is really a good thing. And I think that much of the reason we haven't yet been delivering on this promise is that that was not the bottleneck. That was not the real main pain point. But now that it's becoming that, I think we're going to see dramatic improvements and dramatic shifts in the ways that people think about compression and the kind of new approaches that we're going to see.
So obviously, I'm not an expert at compression, but I could imagine there are issues like, and in fact, I know this, that there are issues about whether the compression loses any information or preserves every single bit, so that when you reconstruct the item, it looks perfectly the same versus there's been a little bit of changes at the edges. I know that's an issue. I would guess that there's also an issue about how quickly you can either compress it or uncompress it, depending on the needs of the users. So are there other important trade-offs that happen when you're designing or thinking about compression strategies?
Yeah, I think that you've touched on the two main sort of axes that we're mindful of when we think about compression and compression algorithms and implementation of compression and hardware. So it's definitely, it's sort of the amount of actual bits that you're going to need for representing the data. It's how fidelity, the level of fidelity, how close the reconstructed version will be to the original, and the complexity. And the complexity of this whole thing is, you could potentially measure it in all sorts of ways, and it depends on the application. And sometimes it's about the complexity of this so-called encoding, like the way in which you take the data and you represent it in bits. Sometimes it's the decoding complexity. How do you take those bits and reconstruct the data? And so, these are the main kind of figures of merit. Another one is the so-called random access, like how easily would it be to, access very specific parts of the data without necessarily having to sort of decompress the whole file.
I just need this part of the document or this picture, this little part of the picture, and then maybe you can save time and not undo the whole thing.
Exactly. So I'm sure that you've encountered this in the context of your work in genomics and bioinformatics. You don't necessarily want to open like a file of a few gazillion gigabytes if you only want to access a certain k-mer that pertains to a certain gene.
So the other thing is, as I think you just referred to, there's an important issue about how complex the data is that you're trying to compress. I know, for example, that if I have a picture that's just a big black box, that you can compress that very effectively into a very small file, because all you have to tell it is the whole thing is black. Whereas if it's an image of the Alps with trees and flowers, so what are the main data types that professional people who are thinking about this are thinking about because of the scale and the volume of those data? What are the important data types to get compression right? I think you made a reference to DNA, and I'd be interested if that's one of them.
Yeah, so absolutely. Genomic data is a whole world of sort of data types and also modes of modes in which you want to be able to access the data that is really interesting, and we can sort of delve into some of that. Also, as I said, multimedia, multimedia compression, both the sort of traditional, data formats, the images, the video, but also increasingly, now it's a wild west where everyone's talking about the metaverse. So in the context of AR and VR and point clouds and mesh clouds.
So AR and VR is augmented reality and virtual reality.
Exactly. And then related is, let's say, point cloud data, which is captured by, all these images, all these devices now that can, for every point in space, can give you a lot of information, even beyond RGB, the red, green, and blue, but information about temperature and all sorts of other sort of interesting spatial information about the environment. And so this is a wild west in terms of the data formats, which haven't been standardized yet. And also in terms of the volume. Again, you're getting, orders of magnitude higher volume per unit time and per piece of space than with the kind of more traditional multimedia technologies. And, so the fun thing for people like me is that there's a lot of room for compression with, also some very low-hanging fruit.
So on those issues, that was great because there's all these different kinds of data that we might care about. And I know that when I compress things, I have standard programs on my computer that I use. And it's always the same algorithm, no matter whether I'm compressing an image or a DNA file or a text file. Are we moving towards a time where you'll use different compression programs or strategies for different data types? Or do we still want to look for the kind of just use this and don't worry about picking and choosing to match your type of data?
Yeah, that's a good question. And I think, like, for people like me, much of it, in general, I should say, there's a sort of a trade-off between, how generic and unspecific you want your compressor to be and how well it's going to do on your specific type of data. But there's a field in information theory, which is sort of the more mathematical part of data representation, and in particular of compression, called universal compression. And that's about understanding how to construct schemes, compressors that will do essentially as well on your data as if they knew that, let's say, now we're dealing with genomic data. But will be, won't need to know this information a priori. And so we haven't yet, in some sense, we haven't yet delivered fully on the potential and the promise of this theory. So I think people who do research now in information theory, some of them are worried about, or they work on developing compressors that will be essentially as effective for compressing all these different types of data as the current very data specific schemes are. Like, for example, that if you tell a compressor that I'm now working on genomic data, and or let's put it this way, if you know that you're working on genomic data, right, by now, that you have access to schemes that are very specific to that. Instead of using gzip, you're going to use, let's say, a compressor known as Spring in the context of FASTQ data, so-called, and which is data that pertains to reads that come out of your genomic sequencer, and that will give you orders of magnitude better compression than gzip. And so, I guess to your question, currently we know that there's a lot of potential for doing much better compression than with the generic schemes, but I think it's going to take a while until the sort of the standard compressors out there that are kind of off the shelf do as well as the specific compressors for specific data types. But there's no reason why we shouldn't and wouldn't be able to get there soon.
This is The Future of Everything with Russ Altman. More with Tsachy Weissman next on SiriusXM Business Radio, Channel 132. Welcome back to The Future of Everything. I'm Russ Altman, and I will continue speaking with Professor Tsachy Weissman of Stanford University about information storage. I will ask Tsachy about his experiments that show that the human brain is much better than our current algorithms at information compression, and how we can take advantage of that knowledge to invent the next generation of algorithms. I'm also going to ask him about how biological molecules like DNA might be a storage solution for the future.
I mean, on various levels. One is in the context of multimedia compression. We had some real fun working with a bunch of high schoolers on gleaning insight as to how humans perceive and describe information in the context, let's say, of image compression. So if you look at our current storage technologies, right, there are all these algorithms that some of our viewers might know of, WebP, MPEG, and so on, JPEG. And on the other hand, if you look at how much time and bits you would need as a human to describe what you're seeing in an image in a way that another human can, maybe just read the text of your description and reconstruct, what these high schoolers actually have shown us in very quantifiable ways is that the human, as both an encoder of information, when observing an image and then required to describe it, let's say in text, and then another human as a decoder of information that looks at the text and reconstructs an approximate version of the original image, human encoders and decoders are orders of magnitude better than our current technologies for representation of multimedia data. Specifically for images, you can show, and these high schoolers have shown, that to achieve essentially the same level of satisfaction in the reconstruction between the original and the reconstructed image, humans need 3 to 4 orders of magnitude less bits.
So this is like 1,000 or 10,000 times less.
Yes. No, sorry. So maybe I'll scale it down a bit. Currently, you know what? Yes, I'm going to stick with that. Yes.
Okay, so that's and now let me make sure I understand it, because that sounds like unbelievable. So somebody could listen to this podcast and say, yeah, 2 guys were talking about compression. It was pretty good. That's a nice compressed version. But there's a lot of loss. There's all the great stuff that you're saying. So when you're talking about creating images, did they say stuff like it's a picture of a fire engine? Or did they actually give enough information for the other person to imagine the picture and exact more about what it was actually like?
Yeah, so it's the latter. It's basically, we took these poor kids, these poor high schoolers who were so highly motivated because they wanted us to write good letters for their college applications, and they would spend literally whole days writing full text descriptions of what happens in an image in a way that then another high schooler had to read and reconstruct at a very high level of detail. So all the things that you would care about as a human in your reconstructed image were there. And then, but overall, the size of this text, which represented the data, was these orders of magnitude that we talked about, less than the size of the file if you compressed it with the existing technologies and wanted to get a reconstruction even close to the same level of satisfaction that people had from this sort of human compression.
And so as an information scientist, when you see that, you think, I should be able to figure out algorithms that can emulate what that high school student was doing, and then I'm going to be able to benefit from these huge compressions that essentially they're demonstrating empirically.
Precisely. I mean, we have all these, all our friends and colleagues from CS and even from my own department, from EE, who are promising us that they can deliver with deep learning the kind of performance that humans can attain. So why not try to emulate these human compressors and decompressors with our technology?
Great. So in the last few minutes, I don't want to miss the opportunity to ask you about new storage media. So we all know about hard drives. Some of us know a little bit or remember CDs and DVDs. What are the frontiers of the kind of media where we might be storing information, with low energy and good reliability and all the things you've been talking about previously? Where is the future?
Yeah, so this actually relates to our previous topic in a sense, because we talked about human-inspired compression. Well, here you can think about human and biologically inspired storage media. We know that, for example, the DNA is an extremely efficient molecule for representing information, both in terms of the density of information, which currently, if you think of representing information in the order in which you synthesize the A, G, C's, and T's, a DNA molecule, then you have 2 bits per every base pair. And if you were able to do that reliably, you could get an information density which is probably 6 to 7 orders of magnitude higher than with our current silicon-based technology.
I want to make sure that we're clear. You're not talking about necessarily using the DNA to store information about the processes of life, which is what DNA currently stores. You mean we might be able to store images and documents and all the things we put on our computer using DNA as the way it's encoded? I just want to make sure.
Absolutely. And not only we might be able to do that, but we are already doing this. It's just that current technology for doing this is very costly and time-consuming and unreliable. So it takes you a lot of time to synthesize the DNA in a way that represents, this information, which could be totally different, unrelated to biological information. And then also the reading is fraught with error and with sources of corruption that make this currently a problem, which is very interesting from a research perspective, but not yet a technology which is scalable and realistic today. But if you ask me, 2 decades from now, very likely we're going to see this technology replacing much of our current silicon-based technology.
That's just fascinating because, especially since, our bodies solve some of the problems that you've just outlined by having a zillion copies. Literally every cell of our body has our genome, and that's how we make sure we don't lose it all. So You can imagine these might be strategies.
So this touches on a couple of additional points. So once we're able to get our sort of synthesis technologies to represent the information in such a fine-grained way, just literally in the A, G, C's, and T's, we know that it's an extremely stable molecule. I mean, the mammoth DNA was found and reconstructed after tens of thousands of years without any sort of maintenance, without server farms that have, controlled temperatures and so on. And also, as you alluded, the ability to replicate this information is so, would be enhanced so significantly with this new technology.
Thanks to Tsachy Weissman. That was the future of information storage. You have been listening to The Future of Everything with Russ Altman on SiriusXM Business Radio, Channel 132.